I'm Robert Lee Kilpatrick. I'm the chair of the Health and Medicine Member-Led Forum here at the Commonwealth Club. I'm also on the Board of Governors, and there's a bright light there. And I would like to welcome all of you here in this room for a live program, and also those of you who are coming in over the wire, watching it on YouTube, on your computer. So I'd like to introduce the club very quickly. This may be your first visit. The Commonwealth Club was founded in 1903, and it is the oldest and the largest public affairs forum in the United States. It's kind of a who's who, some of the most important thinkers, activists, people who are making a difference in our lives in this country have come here and spoken to live audiences. When COVID happened, the city of San Francisco closed our doors. And so this a phenomenal team here, for the first time in our history, went online. And all of our programs for almost 3 years were completely online. There were no in-person events. But now we're back in a hybrid format. And tonight, I want to thank the amazing technical team here at the Commonwealth Club, but also the phenomenal team at the Gladstone Institute, run by Anne-Marie Rooney, and maybe her team could quickly stand up. Round of applause. They have worked very, very hard with me to deliver this event and with the team. So, without further ado, I'd like to introduce Dr. Deepak Srivastava, MD. Many of you know him, but some of you do not. He is the president of the Gladstone Institutes, which is not far away, just over here in Mission Bay. He is the director of the Roddenberry Stem Cell Center, and also a professor of pediatrics and biochemistry and biophysics at the University of California, San Francisco. So today we're going to hear all about a revolution in medicine, the science fueling a new age of cures. Thank you very much.
Thank you very much, Robbie, and thank you all for braving the weather and being here today. You guys are the committed diehards, so hopefully you'll enjoy what we have to talk about today. So what I'd like to spend the next half an hour or so on is in sharing with you the reasons for the excitement that we all feel in science and medicine right now, because we are just at the cusp of a revolution that's occurring that we recognize in science and medicine, but I don't think it's really hit the public as yet, but it will in the coming years. And I'd say right now, having been a physician for over 35 years now, I'd say we do a great job in medicine right now. And by and large, for most diseases, we do better today, much better than what we were doing 20 years ago, across the board. And I think that's great. But for most diseases, the way we approach those conditions is really pretty much the same as what we did 20 years ago. We just do it all a lot better. But the paradigm's really the same. And what I'll show you is that that's what's changing right now. And 20 years from now, medicine will be almost completely unrecognizable compared to what we do today. And it's because we will be addressing human disease with completely different paradigms. And I'm going to share with you today what's driving that big sea change right now. Now, when I thought about how to describe this new world of really shifting from managing disease to curing disease, which is what you'll hear about, it reminded me of a patient I had some years ago who came into my clinic and had a terminal illness, and there was really nothing we could do for this individual, and I told him that. And of course he said, "Doctor, please, isn't there anything I can do? I'll try anything." And I said, "Well, I don't really think we can." He says, "Please, there must be something." So I said, "Well, there is something, but I don't think it's going to work." And he said, "I'll try it." So I reached up on my shelf and I brought down this bottle and I poured some of it into this glass. And I said, "Okay, look, I'm going to turn the light off. And when I do, you need to drink this as fast as you can." So I flipped the light off. He drank that, threw it back, and then he spit it out and said, "Doctor, this tastes like whiskey." And I said, "Well, it was a shot in the dark." But I tell you that story not just as a joke, but a lot of what we do in medicine right now is a shot in the dark. We have to do something, but for so many conditions, we just haven't known enough to do more than a shot in the dark. And it's a little bit more than a shot in the dark, but for many things, like take cancer, for example. We give chemotherapy in many cases that will kill a whole lot of cells, cancer cells and our own cells, right? It's we're going to look back and say that was a shot in the dark. And so that's what's fundamentally changing, and it's what I want to describe to you, how and why. So if you step back and think about disease in a very maybe oversimplified fashion a bit, most, not all, but most human disease falls into two large categories. Either people have a disease because they've lost the cells that should be doing their job, and they're no longer in the body, they're gone. Think Parkinson's, diabetes, or the cells are still there, but they're malfunctioning. They're not doing what they're supposed to do, either because their wiring has gone haywire and they're not executing what they're supposed to do, or they have a genetic mutation that is causing those cells to malfunction. In either of those cases, we'd ultimately want to be able to hack the code of what's going wrong and fix it. And so, if you wanted to, not right now, we largely accept that those are the situations. We manage through the disease best we can, accepting that either cells are lost or they're malfunctioning, and we do the best we can. But if you wanted to think about actually curing those conditions, it's not that complicated. If you've lost cells, then, of course, you want to replace those cells. And if the cells are malfunctioning, well, you want to go in there, figure out exactly why, or edit the genome and change the code, and then correct those so they now function just fine. And if you could do those things, then you would essentially have cured the disease. And the reason we can't do that right now, haven't been able to for most diseases, is that we haven't had the technology to do either one of those things. And that's what's changing right now. And the reason it's changing is what I like to call the 3 R's. The 3 R's to hack the code of life. So we all learned about reading, arithmetic, and what's the third? Writing. When we were young. See, I already forgot because I think about now these. So the same thing applies here. The first thing we have to do to be able to achieve what I just showed you on the last slide is to be able to read our genomes. And when I say read, I don't mean just reading what letters there are, but understanding the genome. And that we're beginning to do. But if you could just read and understand and not do anything else, it's just a good to know feature. But what if you could not only read it, but then know how to reprogram the genome to make it do what you want it to do? That would help. And what if you could not only do those two things, but then you could go in and actually rewrite the genome to make it say what you want it to say. Change the letters, change the words. And that is what's happening. And they're happening, each one is so powerful, but if you combine those three, then they're exponentially more powerful, and I'll show you exactly how. And it's the combination of these three approaches that is really driving this sea change in our science and medicine. And that is really being driven by technologies that are allowing us to do each one of these things. And to read the genome, we really have taken advantage of the advances that you hear about every day in artificial intelligence. Each genome is composed of 3 billion pieces. And it's with AI that we're beginning to not only understand what that genome is trying to say, but also how it's helping us understand it. And then to reprogram the genome, we've really been able to take advantage of a new stem cell technology that I'll describe to you that allows us to take cells, even from any one of you, and reprogram them to make your own stem cells. And then finally, we've been able to rewrite the genome through a technology known as CRISPR that allows us to go with precision and edit the genome and change the code back to whatever we want. And it's those three together that is driving this change. And we're fortunate at the Gladstone Institutes to be leaders in each of these areas. And I want to share with you briefly how we're putting these three things together to address disease at Gladstone. And so I think many of you are familiar a bit with Gladstone, but let me just take a few moments and describe to you how I see where we fit in the broader ecosystem. So the Gladstone is a nonprofit biomedical research institute that's independent, freestanding down here at Mission Bay, as you heard. We're about 35 laboratories and 700 employees, and they're not just 35 of the best laboratories in the world, but rather they're 35 laboratories organized into highly collaborative teams to tackle a few key diseases. And these are really the major unsolved diseases of humankind. And those include heart disease, neural diseases like Alzheimer's, Parkinson's, viral diseases, initially HIV, and now so many others that we have to worry about. And then diseases where our immune system could be leveraged to both kill cancer cells, but also have our immune system not kill our own cells, as occurs in autoimmune disease. So those are the four key areas where we've decided to focus our energies. And then we weave together with experts in these areas, experts in some of those key technologies that I mentioned, so they're seamlessly integrated with the questions around those diseases. And now we are independent from a governance standpoint and a financial standpoint, which is wonderful, but that model, as successful as it's been, does not operate in isolation, and I don't think would be as successful in isolation. Part of our success is because of our ecosystem here in the Bay Area. And we've had a long-standing 45-year close affiliation with UCSF, which is right across the street from us at Mission Bay. And in recent years, we've forged similar affiliation agreements with UC Berkeley and Stanford, recognizing that there's not just one world-class university nearby, there are three. And we're so lucky to have that here in the Bay Area. And then our tagline, if you've seen, is Science Overcoming Disease. And while we do deep discovery science around disease, if we just kept making great discoveries after great discoveries and they sat on the shelf, we would not be fulfilling our mission. And so we're very proactive with the venture capital community and the biotech and pharma community in the Bay Area, and we're lucky to have one of the largest in the world, to get our discoveries out into clinical trials. And we've spun out over a dozen biotech companies here in the Bay Area just in the last 4 or 5 years. And so that's how we're organized, but as great as that is, I think that the secret sauce of what makes us so special and has made it so successful is actually our culture. And it's a culture of caring, of creativity, of collaboration, and of risk-taking. And it's a culture of fun. I'm a deep believer that if you love what you do and you do it with people you love doing it with, you're going to do the best that you can possibly do. And that's the kind of culture we've tried to create at Gladstone. So I can stand here and tell you all these things, but I want to take a moment and show you a video that we made recently where this model has been so successful that we've decided to scale it by about 50%, and so we're expanding our effort at Gladstone. And so we made a little video to help describe who we are and what we do, and I want you to hear directly from some of our scientists and from some of the people that we're affecting by our science. And so if you'd indulge me, we're going to play a little 5-minute video here for you. I think we're at a moment in time in science and medicine where we have the opportunity to no longer accept that people have diseases.
We're really at the start of a revolution in medicine. We can cure human diseases. And this is not a fantasy, it's actually now a reality.
when my husband was diagnosed with Alzheimer's disease. I felt, my life was never going to be the same, or his.
My whole life, I thought I was going to be a professional football player, and on September 10th, 1994, I went in to make my 24th tackle of the day, and I had a C4, C5 implosion of the vertebrae, and that rendered me paralyzed.
I had a normal pregnancy, normal delivery, and then when she was about 12 hours old, they said, oh, she's a little cold. She was born with a single ventricle. Katie's heart just beats once with a huge beat. If you took a stethoscope to it, it's quite an interesting sound.
At Gladstone, we have two missions. The first is to solve some of humankind's most devastating diseases and bring them to cures. And the second is to train the next generation of scientific leaders.
We are in an era where biology can help patients in ways that have never really been possible before.
Disease has two fundamental causes. Either cells have been lost and need to be replaced, or they've malfunctioned and need to be fixed. Because of discoveries pioneered by Gladstone scientists, we can now do both. Reprogram our cells to reverse damage or decay, and actually edit the code of life to cure disease. Combined with giant leaps in the power of AI, we can now see more deeply into the causes of disease and move faster, several magnitudes faster than ever before.
A lab doing an experiment in an animal model or a cell line might be able to investigate one hypothesis every couple of years. In my lab, using computational approaches, we can test millions of hypotheses in one day.
We have 3 world-class universities all sitting right around us, Berkeley, Stanford, and UCSF. And it's by putting all those together that we're really able to make the breakthroughs that will lead to new treatments for patients. That's the value of our partnerships. Beginning as a handful of labs in 1979, Gladstone has become one of the world's leading research institutions, home to more than 600 researchers from nearly 40 different countries in the birthplace of breakthrough technologies. Biologists, chemists, disease experts, data scientists, ranging from graduate students to Nobel laureates, all working together with a single purpose: to overcome disease.
Taking risk in science means not that you might fail. It means that you've tried at something that others were probably not willing to try.
I particularly cherish that we are not doing all the same thing. Having cardio, neuro, data science, and immunologists is extremely stimulating because we can collaborate with them.
We've been able to collect the best scientists in the world to work together with expertise seamlessly flowing between the laboratories.
I don't think there has ever been a more exciting time in neuroscience than now. We've seen successes in the clinic now that allow the brain to recover and repair itself.
Bit by bit, we're getting closer, and Alzheimer's will be like any other disease that we have found chemistry for to defeat.
My daughter would not have survived without this research, so I'm very passionate about it. If more people knew what was being done and how that was really, not to be too grand, helping mankind.
You hear about the Industrial Revolution, but this is going to be the medical revolution.
We know every day that we can speed up our discoveries means thousands of lives we can save.
For some diseases, we have passed the half point. Now we can see the goal. But for many other diseases, the race has just started. We need to run multiple races at the same time. We are tough, but we need support.
Funding that allows us to take risks, to build our team, to scale things up, to go after bold ideas. We're marching towards progress now. We can sprint towards it with this campaign.
What is the power of what we can do right now and the type of people that we have at Gladstone? And these three areas that I mentioned to you that are really driving this change are not only things that we're using, but we've had the good fortune of collecting the key inventors of many of these areas, and we have many people at Gladstone training foundational models with AI and developing the new platforms that people around the world will use. And we're particularly fortunate to have the inventors of these key stem cell and gene editing technologies at Gladstone, including Shinya Yamanaka, who invented this approach that I'll share with you to take your cells back in time to become stem cells. And he won the Nobel Prize for this in 2012. And in fact, he trained at Gladstone back in the 90s and is one of the examples of that other part of our mission, which is training the next generation. And Jennifer Doudna, who did her beautiful work inventing CRISPR technology at UC Berkeley, has been running a second laboratory at the Gladstone Institutes for the last 7 years. And that has allowed us to really have these two technologies with the inventors of those across all the laboratories, integrated across all the laboratories. Now, let me start off by how AI is impacting us. So, when you talk about, we talked about those 3 billion parts of the DNA, well, if you were able to decode all of that in a lot of people and then combine that with electronic medical records, you could start to begin to see how genetic variation might contribute to disease. And before I say more about that, I want to make sure we're all on the same page, since I know some of you, last biology you took might have been in high school. This is what the double helix looks like. We have genes are encoded by these double helix. There are 2 copies of every gene in our genome. And then if you zoom in on an area of this, you have the letters that you're familiar with, the A, T, C's, and G's. And the way the code works is that every 3 letters together encodes for 1 amino acid. And if you change just one of those letters, say from a G to a T, that changes the amino acid that's made from that in a protein. And so as that gets read out, you get a chain of amino acids. And if you just change one letter, like you see below, you get a completely different amino acid. And sometimes that doesn't really matter, and it's fine, who cares? But other times, that single amino acid change can so fundamentally change the shape of the protein that that chain gets folded into, that it looks so different that it now doesn't function properly. And the functions of proteins are largely dictated, actually, by their shape. And if an amino acid changes the shape, then it may no longer be able to function. And in fact, many human diseases are caused just by that one letter change out of 3 billion that causes a change like this that results sometimes in fatal diseases. And this kind of variation goes all along throughout the whole genome. So out of those 3 billion, there might be lots of different amino acid changes, some that are important and some that aren't important. But how do we know? It used to be that it took years for someone in a laboratory to figure out how an amino acid changed the shape of a protein. And what AI has done is 2 things. One, it allowed us to first predict what these changes would be, and now we can decode any one of your genomes for a couple of $100. It used to be $1 billion at the turn of the century, and now for $200 or $300, we can get the entire genome from any one of you. And that's relatively recent, and so what's happening now is we're getting the genomes of lots and lots of people, because it's less than most blood tests that you might do. But as we get this information, we're going to have not just 3 billion of these pieces of information from one person or 100 or 1 million, which is about what we have now, but it's estimated over the next 5 years, by the next decade, we'll have gone from 1 million genomes that have been decoded to 100 million at least. And so what's going to happen then is that we're going to know the genetic variation at scale. And when you marry that with, as I mentioned, electronic medical records, you can start to ask, if somebody has this set of genetic variation, how does that affect their outcome for various diseases? And you can imagine how much information that's going to take, it will be. And if we hadn't had the advances that have come up in the AI field just in the last 2 years, I'd say, this would be an insurmountable problem. We'd have a lot of information and probably not know what to make of it. But that's all changed now with the advances in AI. We're going to be able to understand at scale what genetic variation is associated with what disease outcomes. And that's what's going to lead us to the targets to go after to try to fix those diseases at their root. Now, many of those genetic variations, as I mentioned, are going to lead to changes in the protein shape. And fortunately, just in the last year to two, there have been advances in AI that have led to a predictive algorithm that can say, if the DNA sequence changes this way, I predict it's going to change the shape of these proteins. And what used to take 3 or 4 years to figure out the shape of one protein, in one fell swoop, one day, a couple of years ago, we knew the shape of 100 million proteins. It's phenomenal. That changed everything. In fact, the team that did that received the Nobel Prize last year for it. And so we're going to know all the shapes of the proteins, and not only know the shapes, but then that tells you how you fix the shape. So if you know that there's this divot here that shouldn't be there, well, maybe we can design a drug to go in there and fix the shape that went wrong, and now you've fixed the protein, you've fixed the problem, you've cured the disease. That couldn't happen. None of this could have happened without the advances in AI just in the last year to two. And so we're in a position now where at scale, we're going to be able to take all these steps, and that's happening right now, right here. So let me put all this together for you in a concrete example, in this time around Alzheimer's disease. Now, I imagine everybody in this room virtually knows or has been affected by somebody in their life with Alzheimer's disease. It's a terrible disease that now affects 7 million Americans, and it's expected to go up to 16 million by the middle part of this century as people get older, because this is a stunning statistic. Nearly 1 out of 2 people over the age of 85 will have Alzheimer's. Think about that. In a day when so many people are living healthy lives at 85, this is a stunning statistic. And the sad part is, so far, almost every drug that's gone into the clinic has failed, and the only couple that have worked have had marginal success with just slowing the progression of the disease by about 25%. That's clearly not enough to address this problem. And so this is by and large a problem where cells are malfunctioning. They're there in the brain, but they're malfunctioning. And so one thing that we do know about this disease is that there is a genetic risk factor that's very well known. And that is a gene called apolipoprotein E. I'm going to call it ApoE for short. And ApoE comes in actually a couple of different forms. And they differ just by 1 or 2 amino acids that dramatically change the shape of this protein. Most of you, about 3/4 of you in the audience here, have what's known as ApoE3. And that's good. But about 1/4 of you have one copy, one of your 2 copies is ApoE4, and you have a 3-fold increased risk of Alzheimer's, which is a pretty significant increased risk. Now, 6% of you in this room right now have 2 copies of ApoE4. And unfortunately, those individuals have a 12-fold increased risk for getting Alzheimer's. That's huge. It's still the single biggest genetic risk factor for any common disease that we know of. And so the question then becomes, why does this occur and what can we do about it? And we've been fortunate at Gladstone in that we've had the world's largest and deepest group of scientists studying this protein for a long time, because it was also involved in cholesterol regulation, which is what Gladstone is actually founded on decades ago. And so one of our investigators, Yadong Wang, decided to dig into this a little bit deeper using all the tools that I just mentioned. And so there's a repository that's been set up for people to be able to donate their brains when they die if they've had Alzheimer's disease. Unfortunately, a lot of people do this. And so Yadong took a group of brains from people who had Alzheimer's with an ApoE4 mutation and those that did not have an ApoE4 condition and were normal. And then he simply asked, looking at the genes that were turned on and off in these brains, what's different? And he saw a very clear difference in the pattern. And I'm showing you these red and blue maps here. I won't go into the details, but they just signify what genes are active in red and inactive in blue. And you can just appreciate that there's a difference in the pattern in the diseased brains versus the non-diseased brains. And so that ends up correlating with the disease process. And so if we know that, then imagine if we could find a drug that would just shift that pattern from the abnormal state back to the normal state. That drug might be able to stop or reverse the Alzheimer's process. And so Yadong decided to ask if he could find such a drug. And to do this, one would ideally want to test drugs on the brain cells from a patient with Alzheimer's. But of course, you can't really take a biopsy of somebody's brain. And that's where this stem cell technology comes in. And I want to share with you that now, and we often refer to it in our field as cellular reprogramming, because the key discovery here that allows us now to test drugs on a brain cell from a patient with Alzheimer's is the following. And this is what Shinya Yamanaka invented that won him the Nobel Prize. And that is that he found a way that we could take a teaspoon of blood from any one of you, or a skin sample, and put that in the dish, and just by adding 4 proteins, just 4, that were so powerful they could go in your genome and flip a bunch of switches and turn thousands of genes on and off, we could reprogram your adult cell and take it back in time. So now it behaved just like your own embryonic stem cell that was in you when you were only 5 days after being fertilized. It's phenomenal. And what that means, the property of a cell like that, which is what we often refer to as an embryonic stem cell, is that it can turn into any of the cell types in our body. And so Shinya, at the time when he invented this, he called these induced pluripotent stem cells, meaning they have the potential to turn into all the different cell types in the body. And this actually, he made this discovery around the time of the iPhone coming out. So he did a play on Apple and called this little iPS. So I'm going to refer to these as iPS cells going forward. And so the beauty of this now is you can take a cell from a patient with Alzheimer's, turn it into a brain cell, and now have in front of you, if you want, a cell from a patient with ApoE4 variation, and now you've got cells in the dish right in front of you that came from the patient with disease, have the genetic variant you want to study, and now you can both figure out why is that cell going wrong, and can I find a drug that would reverse that? And so Yadong did exactly that. And he took these disease cells in the dish and then used a computational-based approach to screen through 1,300 drugs that have been approved by the FDA sometime in the past. So this is the whole list of drugs that are out there for other reasons, but it means people have been taking them for a long time. And then he asked if any of those drugs might reversed that step, tested it experimentally, and lo and behold, from that came a handful of drugs that looked like they were reversing that pattern. And one of those drugs that was particularly powerful is called Bumex. And this is a very highly used drug that is a diuretic, means it makes you pee more, and to use a technical term. And it's been used for decades for heart failure, for hypertension. And that drug in the human cells in a dish could make those cells better. He tested that drug in an animal model that he had made where the human ApoE4 gene is in the mouse and they get memory deficits, and this drug worked in mice to help their memory. But I should say we've cured Alzheimer's in a lot of mouse models over the years. And so what we really want to know is what does this do in humans? And for there, we had the advantage that, as I mentioned, this drug's been used in people for 4 decades. And so now we have electronic health records. You can go to those patient databases and say, and pull out of those and say, give me millions of patients who've been on this drug and tell me what is their risk for getting Alzheimer's. Give me millions of people who never were on this drug and what is their risk for Alzheimer's. And lo and behold, when we did that, it turned out that people who had been on this drug for other reasons in various cohorts had an up to 70% lower incidence risk of getting Alzheimer's being on this drug. That's amazing. It's a huge reduction. But of course, it's just an association. That doesn't mean it's cause and effect. And so what we really want to do now, and this gives us the impetus to do it, is a proper clinical trial with this drug. But because it's already known to be safe and been in people, it quickly moves to an advanced stage. And Yadong has set up a clinical trial already with Stanford and UC San Diego, and they've already enrolled half of their projected individuals. And in the next 18 to 24 months, we're going to start getting readouts of that, and we're going to know if this drug really does confer that lower risk, but by all indications, this is a very promising drug. And so this just gives you an example of where we've used a bunch of different of these technologies to really come to this conclusion, which we never could have if we didn't have those. Now, as you can imagine, when we published this, it got a lot of press because it's an exciting result, the big reduction in the risk for Alzheimer's. But about 2 months later, another group from the Cleveland Clinic took a slightly different approach, but published something similar. And that discovery, a bit unfortunately for us, got a lot more press because they came to a different drug. And you can imagine why that got a lot of interest. I don't know if they've started a clinical trial with this or not, but I bet they'll have a lot of people enrolling. But in any case, I hope that gives you a flavor of what we can do about sort of lowering, fixing cells that might have gone awry and malfunctioned. I want to turn now to this other side of this disease, which is if you've lost cells and you want to replace them. Well, the same technology of reprogramming your cells to make your own stem cells applies here because we can make virtually every cell type in our body in the dish now, and they could be your own cells. And so these cells could then, you could imagine, transplanting back into individuals who have lost cells, and now you might be able to cure them that way. And over the last many years, we've worked hard as a field to be able to efficiently make all these different cells, and we can do that for virtually almost all human cell types. I'm going to show you one of those, which is a heart cell, because it's the most visually pleasing cell, not just because I'm a cardiologist, but because heart cells actually do something. They beat. And so I'm going to play a video for you here in a second, but what you're seeing here are actually thousands of cells. Each cell is very small on the screen, and they've electrically connected with each other. So they beat in synchrony, just like our hearts do. And I'm going to play the video, and you'll see this. It's really quite remarkable. These cells used to be on somebody's skin. And now they're beating just with their own rhythm, just like our hearts would. You can see the rhythmic contractions, which is really a phenomenal thing. And we can grow these to scale. We can grow billions of these now. And so, like this, we can grow a number of other cells. And already today, there's a host of diseases, some of which are shown here, but not all, that are already in clinical trials receiving cells for transplant, either induced pluripotent stem cells or iPS cells, or embryonic stem cells that are made from human embryos. And in various forms, these are being at various stages of clinical trials. And I should say, being in California here, the California Institute of Regenerative Medicine, which is taxpayer-based funded, so you all are funding this, has initiated over 30 different clinical trials here in California using embryonic stem cells or iPS cells for various different diseases as well. And so not all of these are going to work, but they'll read out now over the next 2 to 3 years. Most of these will read out. And I'm already seeing some beautiful data around corneal transplants, where you can fix one eye and leave the other eye where people are blind and people are able to see again. So this looks like it's working. I just saw early data around Parkinson's disease, where it's a small number right now, but their movement is improved and it's looking very promising. And I just want to share with you one area that is probably the most advanced, that looks really, really encouraging, that I'm really excited about, and that's around diabetes, type 1 diabetes. And I'm sure many of you know people with type 1 diabetes. It's fairly common. These are conditions where the insulin-producing cells in the pancreas die, and people can get by with insulin injections, but they have long-term complications as they get older. And so now we can make insulin-producing cells in the dish from pluripotent stem cells, either embryonic stem cells or induced pluripotent stem cells, and we can make these at scale and then transplant them. And so I want to share with you some results just released a few months ago from a company called Vertex in Boston, where they've done this trial. What I'm showing you here is a patient's data over a month period on the bottom, on the axis at the bottom, and the vertical axis is measuring their blood glucose levels every day. And you can see it goes up and down throughout the days, throughout the month, and that gray area, the target area, is where it is normal area. And even with insulin injections, you can see it's going up and down all the time. And that's not great, but that's the best we can do right now. This patient got transplanted with insulin-producing cells that are derived from stem cells, and 4 months later, it looked like this. A lot more time in that gray area that are green dots, but still spiking up every now and then into that bad area. Same patient 8 months after transplant. Look at that. Look at that. That patient is cured. 100% of the time in the normal area, no insulin injections. This is one patient. They reported their first 12 patients. 11 out of those 12 are either off insulin or almost off insulin. This is going to be cured. There's one caveat. These cells were not their own cells, and so they had to be immunosuppressed to get this. And honestly, it's not a great thing long-term to be immunosuppressed when you could be just taking insulin injections. And I want to come back to that in a moment. Now, so far I've told you about how we can use stem cells, take cells from the adult, take them back in time, turn them into the cell type we want. But what if we could avoid one of those steps and actually take an adult cell and directly go to the cell type we want without it ever having to become a stem cell? In this case, maybe a heart cell. And what if you could turn it into a heart cell without a stem cell stage, not in a dish, but actually in the body itself, right where they start off? Because if you could do that, particularly in the heart, then maybe you could regenerate the heart from within. And I want to share with you a story now about how we've been able to do that, namely to address a condition we call heart failure, where the heart simply has lost enough muscle that it can no longer support the pumping function it needs to support the body. This is a very common condition. It's a leading cause of death worldwide. There are 25 million people affected across the globe with this condition, and it's because the heart has little to no capacity to regenerate itself. Now, the end stage of this disease is where you need a heart transplant, but even in the United States, there are only 3,000 heart transplants done per year. That's it. And many countries don't do it at all. And so we've been eager to see if we could somehow take the scar tissue in the cell, in the heart, right where it is, and convert those into new muscle. And it turns out that there's a group of cells called fibroblasts, because they make fibrotic tissue in the heart, which is a scar, and they're very abundant. It turns out that our hearts are only half muscle. The other half are these cells that make scar, but they're also important for the normal architecture of the heart. But they're right there. There's this reservoir of cells that are right there for us to call upon. And so we asked some years ago, could we somehow convert those cells right where they are into new muscle? And it turns out it's not that hard. When we introduce just 3 sort of master genes that go and flip switches all over the genome, we could convert these fibroblasts into beating heart cells. And so we did this now in the heart, right where these cells are. And amazingly, we are able to get these scar-forming cells to convert right where they are into new beating heart muscle and regenerate the heart from within. And this has worked in mice, in rats, and in pigs. And some years ago, we put this into a startup biotech company that we call Tenaya Therapeutics here in South San Francisco. And they are now doing all the diligent work, that's hard work, to get this into a real therapeutic and get it into the clinic. But this gives you a feeling of how we can go from a deep understanding of the problem and be able to basically reprogram ourselves and make them do what we want them to do and regenerate that way. Now, finally, I want to touch on this last member of this triad, which is the gene editing technology. And you can think of CRISPR, which is the acronym that we use for gene editing, as a molecular scalpel, if you will, where unlike surgery we might do on people, we're doing surgery on the genome, where we can go with great precision anywhere we want in the genome and cut the genome. And when we cut the genome, two things can happen. It can either randomly repair itself, and that kind of screws up the gene, which sometimes is all we need to do because that gene's causing trouble. Or we can go in there and actually correct a letter so that we go from a typo to now not having a typo and correct the gene mutation. And this is invented, as I mentioned earlier, by Jennifer Doudna, who's at Berkeley and at Gladstone. And I want to share with you one way in which this technology is merged with the stem cell technology I mentioned in a useful manner. And that's shown here. So the reason that you reject somebody else's cells is that your body mounts an immune response against those cells. And we actually know now what parts of the genome are controlling that immune response. So what if we could go in there in a stem cell and edit out all the parts of the genome that would instigate our body to reject it? Then you might be able to create kind of like a blood bank where we have ABO blood types, and you're blood type A, you go get blood type A off the shelf, and now you're not going to reject it. Shinya is actually trying to make the same thing with CRISPR with these iPS cells, and he estimates that in a homogeneous population like in Japan, that we could, about 10 lines would cover most of the population, 90% of the population. The United States is a bit broader, and we'd probably take 100 lines, but it's very doable. And if you could do this, you remove the risk of rejection. And then, things like I showed you with the diabetes, you'd remove that whole issue of immunosuppression. The other way we're using this at Gladstone is to fight cancer. And one thing we've been able to do is to take immune cells out of the body, put them in the dish, use CRISPR to engineer them, to then be able to go and recognize cancer cells and put them back in the body so they can go hunt down and kill cancer cells. And this is working beautifully in mice, and we're just starting now clinical trials with this effort, both to kill cancer cells, but also to engineer them so our immune cells don't kill our own cells, like I mentioned, for autoimmune disease. And then finally, I want to share with you that it's quite remarkable to me that in 12 short years between the year that Jennifer Doudna invented this technology, we actually have this technology being used in people as a therapeutic. And that is being done for sickle cell disease. This is a really horrible disease. As a pediatric cardiologist, I taken care of many of these kids. It's the most common inherited blood disorder. Kids come into the ER with bone pain and organ failure. And the sad part is we've known the genetic cause of this disease for 50 years. This is among the first genetic diagnoses we ever made. And until last year, we could do nothing about it. But in 2024, this drug, a drug using CRISPR, was approved for therapy because the first 75 people tested in a clinical trial, 74 of those 75 with sickle cell and a related disease called thalassemia were all basically cured. And so FDA approved this in 2024, and this is a disease that people no longer have to suffer from. And so what I hope I've shown you is why we're actually at this cusp in medicine, where we're going to be able to, not all diseases, but many diseases, no longer have to just manage those, but we can now start to envision a future where we actually cure those diseases. I think we can envision a future where a child can open her eyes and for the first time actually see this beautiful world that we all get to live in. I think we can envision a future where a father can ditch his wheelchair and actually chase after his little girl. We can envision a future where a mother can actually look her daughter in the eyes and remember her name. I think we can envision a future where for the first time in human history, we no longer have to accept our genetic destiny. Thank you very much. I think Robbie's going to come up and we'll have some time for some question and answers.
I have so many questions, and I bet the audience does too. I'm going to combine a set of questions into one question with a few punctuation, maybe commas. So the three questions combined to one are, this looks expensive. So if you think about funding from the public, from the government, from philanthropy, from deals with biotech companies, whatever, what can you tell us about the future of funding for the expansion, and comma? And it sounds to me like you are accelerating the process of everything, so it's speeding everything up. And also, the sickle cell is an example of bringing cures to real people like all of us in this audience. So funding, scaling and speeding, and then treating people in the real world. What can you say about all of that?
Yeah, well, those are great questions. I'll take them one by one. So I mentioned, I think on one of my slides, that our annual budget at the Gladstone Institute is about $125 million, which is a lot, but I think we get so much done for that amount. And the way we are funded is about 2/3 of that largely comes from the federal government, where our scientists apply for grants and they compete for those. And about $80 million comes from there. Okay. And about the remaining 40 or so comes from philanthropy in various sources. So we raise those dollars year in, year out to really accelerate and push our science. And those dollars usually really go to doing the most creative work that we do and the breakthrough things, because the federal government is very risk averse. They'll often fund the next obvious step. But you see, what we're trying to do here is not obvious. And so it's really philanthropic dollars that drive those early breakthroughs, mm-hmm. and then the federal government falls in. And then about $5 million a year or so comes from our partnerships with the industry and the biotech commercial sector. So that's sort of how our budget works. And I do think that it's working so well that it's incumbent on us to take advantage of this moment in time when we can really make an impact and scale our model, not hugely, but by about 50%, which I think is the right amount. And so that's why we're expanding our footprint of our laboratories and recruiting more talent into San Francisco. And we've launched this capital campaign of about $350 million over the next coming years to acquire more lab space and recruit the new talent.
Wow, so all of us can play a role in that possibly.
We welcome partnerships. So we're fortunate, again, in the Bay Area to have such a wonderful, generous community, and that's why we've been able to do all the great things we've been doing.
So we should tell our friends.
Tell your friends. I would say that the people in all corners of the world in science know about the Gladstone Institutes. I would venture that there are a lot of people in the Bay Area right now who don't know what Gladstone does, and so spreading the word, you all telling your friends, would be a huge victory for us.
So to go back to those two other parts of the question, when you finished your presentation about sickle cell, I wrote down, what did I write down? I wrote down, and this is beyond hope. In other words, it's real. And that was really exciting, and you got a couple of applause from the audience for. So what can you say about that, increasing the pace of discovery, comma, with a view to delivering greater cures for all of us? Are we going to see something over the next 2 to 5 years that will be spectacular?
I think you'll see a lot of things that are spectacular because the pace of discovery is so much faster now in advancement for the reasons I mentioned.
Yeah.
It's not by chance. And I'd say if I was here on this stage giving this talk even 2 years ago, certainly 2.5 years ago, I would still be saying, I hope that someday we can do these things. Things I shared with you are just in the last couple of years, the success. So today I can say it's happening now. And you're going to see over the coming years, one after another disease will get knocked off where we no longer have to accept those. It won't be all, and we'll have failures along the way. And I don't want you to leave here with the notion that, okay, we can cure everything now, because it's not the case. But the roadmap is there now. And so I do think we'll see that. But scaling, you mentioned.
Mm-hmm.
Scaling is still a big problem. And I glossed over this. The sickle cell disease is a great case. Yes, we can cure it, but it's $3 million. And it's labor intensive because we take cells out of the body, we correct them, edit them, and then we put them back in the body in a bone marrow transplant, essentially.
Sure.
And so is that scalable? No. Is it $3 million? Is everybody going to be able to get that in all corners of the world? No. But it's not the how we get there is straightforward. And it's difficult, so we can't do it today. But our lab and many other labs are working on this. And that is, if you could just inject in a vein the machinery to do the gene editing, and it homed its way into the bone marrow where the blood cells are, and edited right there, all of a sudden, that's scalable, because that's cheap. You just do an IV injection of a mixture. It changes everything. And so the real hurdle for the gene therapies and gene editing is delivery. And so there's a ton of effort going on now worldwide to find better ways to deliver things into our bodies. And once we overcome that, then I think all this is scalable.
Right. So the hurdle is delivery. And I was thinking of another question, which was, you presented an amazing array of positive results and also many opportunities. But as the president of the Gladstone Institutes, what do you think are your greatest challenges in the next 2 to 5 years of any kind?
Yeah. We have a lot of challenges because this is hard stuff. Resources is certainly one of them. But honestly, I don't usually feel like resources are the rate limiting step. The rate limiting step is really talent and creativity. Mm-hmm. So, I think a challenge is getting and retaining the most brilliant, most brilliant isn't right, people who are passionate and care and are going to go the extra mile and be creative. That's what's most important. I worry about that. And honestly, I don't worry about too much. What I worry about the most actually is whether or not we're doing everything we can every day to move fast enough. Because, as I said in the video, people are dying from the diseases we study. And you all have suffered from loved ones dying. I have. And it's not okay. So what worries me the most is, are we moving fast enough?
Okay. So you said that one of the, to use a chemical term, rate-limiting steps, I remember from my biochemistry, one of the rate-limiting steps was talent. And I am not inviting you to go down a political road, but indirectly, since you said there are scientists from 40 countries, mm-hmm. So I have a question from the audience, which is, do you expect global collaboration in these fields will increase Or is there a possibility that we could become more provincial and isolated from other countries in the United States in science?
It's a great question. I am concerned about that. There are brilliant minds in all corners of the world, and we have been able to take advantage of that and attract the best minds to come here and do this brilliant work. Science so far has been largely impervious to a lot of the political noise. There's scientists in all countries collaborate, share openly, China, Russia. That is a wonderful part of science. My hope is that that doesn't change, but certainly the movement of scientists from other countries to come here and train. You know, face it, the United States is a place where still a lot of people want to come. And so we've been able to attract minds from all over the world to come here. And that's part of the way we've been so successful in all areas, certainly in what we do scientifically. It would be a shame if there were more barriers erected towards that, but that may be the case.
Okay. So on a different, to go back to the third part of my combined question about delivering benefit to patients, here's a question that I think is a good one. How can we ensure that these amazing technologies reach those most impacted by premature mortality, such as our low-income residents? Because there is this sense in the longevity field and the aging field and all the health span that it's really for wealthy people and that it will not trickle down.
Yeah. It's something we think about a lot, and I know Jennifer in particular, Doudna, from day one of inventing the CRISPR technology has really thought a lot about this, and it's a driving force behind an institute she runs at Berkeley called the IGI. And I think, as I mentioned, if you can lower the cost of the therapies, like with delivery advances, then that democratizes the technology and makes it available all over the world. So that's why we're spending so much effort there. The stem cell field also, if you have to make your own stem cells and then transplant them into you, every one of them is going to cost a lot of money to make, go through a regulatory hurdle. But if you can take cells off the shelf and deliver them and make them in bulk, then the unit cost goes down tremendously, right? The cost of goods. And so that's why Shinya is trying to develop this universal stem cell line. So it's a huge focus of what we do, because that's part of our ethos, is that we don't want to just create really cool medicines that a few people in the world are going to get and say, oh, wow, how great is that? That's not our mission. We want this to be available to people all over the world.
So when you think about bringing the cost down, the dramatic story is that the Human Genome Project was $10 billion for one person's genome. Is that right? And it was incomplete, I believe.
By the time we got the first genome done in 2001, it actually cost $3 billion, and that one person's was about $1 billion if you were to do it then. Now it's, as I said, about a couple $100. And so again, it's a good example of, over time, technology advancing that drives prices down. We see it in all of our aspects of our lives, and this is exponentially so.
So I heard something in the presentation that made me personally quite nervous, and so I'm going to give you an opportunity to clear it up. You were talking about the EPO-E4, and you said, well, if you have two copies, and I think something like 6% of the people in the room, of course I'm thinking, am I part of the 6%? If you have two copies, there's a 12 times higher risk. Is there a way to test this now? Can I run out and go have it done?
You can, yeah. There's a blood test for it. It's simple. If any of you have done 23andMe,
I have.
It's in there.
Oh.
They have it.
Oh, okay. Would they have told me if I had it?
I think they're careful to have people opt in to know.
Oh, okay.
Right? You can imagine why, because, a 12-fold risk, it's still, you might not get it.
Okay.
But it's pretty high, and, so until it's actionable, until we can do something about it, it's a perfectly reasonable approach to say, I don't want to know.
Yeah.
Yeah.
Okay. Well, we've got about, 5 or up to 10 minutes before we get to have our lovely reception and a nice drink. Here's a question that is, it's kind of technical, I think. So here we go. are we able to use cell reprogramming to rejuvenate the optic nerve before or after blindness? I'm not sure about that.
So not right now, but there are a lot of efforts focused on the retina right now. So it's sort of retina. The retina is in the back of your eye, and it feeds into the optic nerve. And there are a variety of conditions where the retina degenerates and you lose it. So a number of groups are trying to do what we did in the heart, and reprogram cells that are already in the eye, in the retina, to either go from cones to rods. You have two different kind of receptors. So to regenerate the lost ones by using the neighboring cells. That's true for the eye. It's true for the ear, for those with hearing loss. There are cells in the ear that could be reprogrammed also.
Mm-hmm. Well, I hope that was a good answer for whoever asked that question. So I was wondering, so you've got at least 2 Nobel Prize winners at the Gladstone, is that correct?
Correct.
Jennifer Doudna and Shinya Yamanaka. How does having those people in the group influence the other scientists, including the youngsters? Do they think, aha, it's possible for me as well?
Well, it's certainly inspirational, and not just because they're Nobel laureates, they're wonderful people. And that's a key feature of everybody at Gladstone, but they in particular are humble and generous with their time. I think having them in their labs there have kept us at the forefront of these technologies because they continue to iterate and develop, as you could probably tell. And that's great. But yes, it's inspirational. It certainly helps us recruit additional talent because people want to be around those individuals in their labs. And I should say that every Nobel Prize represents a huge leap forward. But I think most in science would agree that some Nobel Prizes stand out even amongst those. And I think most would also say that these 2 Nobel Prizes at least stand out in this century as perhaps the 2 most impactful ones, because they've changed everything about how everybody does science all over the world. So it has a huge impact on us at Gladstone very broadly, I'd say.
They both seem to be very good communicators.
They are.
Yeah.
Yeah.
So I have 2 short questions, and then I'm going to ask you for final remarks. Okay. So the first of the 2 questions is we're going to go back to Alzheimer's now. So you've done all this incredible work, your team's institute. Can you say anything to this audience, both in person and online, about what we should be doing to have a healthy brain?
Yeah, there's a lot out there, and but I would say that it's not very much of it is proven to help dramatically.
Okay.
Let me start off with that. But it's also thought that what's good for the heart is good for the brain. Mm-hmm. So that's probably the simplest way to think about it, because what does that mean? It means exercise, eating well, keeping, sleeping well. Sleeping, some of you might know, while you're sleeping is when the brain cleanses itself. And that is very real.
Mm-hmm.
And so getting enough sleep. So it's many of the same things that are important for heart healthiness, which you hear a lot about, that is probably true for Alzheimer's. But I would be wrong to sit here and say that you should be really aggressive about doing all those things and then you're not going to get Alzheimer's, because it's really not that way.
Thank you. So my final comment or question is related to something that you said during your presentations, which I wrote down in scribbling, which I can barely read. But so I wrote down what you said was this is about the power of what we can do right now. And what I'd like to hear from you on behalf of the entire audience is, how can we get more involved with the Gladstone? Because I want to be more involved. I'm very excited by what you've said today.
Well, that's great. Well, there are many ways. Come by and visit, like I said, and learn more about us. Tell your friends. Some people engage with us. So there are various capital that different people bring who engage with us. There's, of course, financial capital, but that's not the only important thing. There's social capital by getting the word out. Sure. There's capital people bring in terms of their expertise, their knowledge. Sometimes it's with our communications area, sometimes it's with our business area and the biotech area, sometimes it's with marketing. And so we welcome all of those things. It takes a real community to do these sorts of difficult things. And so people engage with us in so many different ways. And I would invite any of you who are interested to please reach out, and we're happy to have you be part of our family.
Do you have open house, or, I mean, when you say come by, I mean, you literally don't mean just come by. Hey, Deepak, good to see you. I mean, is there a way, like here at the Commonwealth Club, we have programs or online things. There's a way for us to engage with you?
Certainly, we do a variety of online programming, and at the Institute, we do programs. And so what I'd recommend is if you join our mailing list, every month I send out sort of what I call lab notes, that it's a summary of what I thought was cool that month that came out.
Okay.
And you'll get that in an easy-to-read fashion. And we have a more broad monthly newsletter that goes out called Cell Signals that illustrates all the things that happened that month and scientific discoveries. I try to cull from that to 2 or 3 or 4 things that are really special. And so there are a variety of ways people can keep track. And if you sign up for those, then you'll also get information when we're doing webinars. Next week, we're doing a webinar on viruses, virology. Larry Brilliant, who's here in the audience, is joining us as a speaker in that. So we try to get experts in the community as well to come and really serve the community and educate the community. I've always felt as a scientist and a physician that it's really important that we bring the public along with us on this incredible journey that we're on of discovery. You all pay for this. It's largely, as you heard, your tax dollars. So I'm working for you all. So I've always felt it's important to bring the public on with us on this journey, and I welcome you all to join us.
Well, that's good, because you're buying us a drink tonight. Before we go to your final remark, and that wasn't it, I know you have a final. So on everyone's seat, there's a little card, and that will be a reminder of the Gladstone, that it exists and such. I intend to sign up for your newsletter tomorrow and get more involved. I'm really excited with what I've heard tonight. And I'd like you to just give us some final remarks that we can then take with us out to the reception, because not only will you be there for a while, but many of the members of the communication team will be there, and you can talk to them too about how to get more involved with the Gladstone. I hope that's helpful.
Yeah, that'd be great.
What's your final comment?
My final comment is that there's a lot of noise in the society right now about science and trust. And through COVID, sadly, a lot of that developed. I think my message, closing remark to you all, is that based on what you heard tonight and what you can see is going on, there are scientists all over the world who are working diligently and passionately for you to help you all live better lives. And there should be no doubt about that. And because of the technologies that are developing, including AI, which you hear a lot of the horrible things that AI could lead to, this is one area where it's all good. AI is going to transform our health. It's all good. You should feel really good about that, and you should feel good that you're living in the epicenter of the AI world. San Francisco and the area here is where the bulk of the AI companies and startup companies are developing, and things are just going to keep getting better. You should have trust and faith that the scientific community is working for you, and the future is extremely bright. This is a good news story, period.
So, on behalf of the Commonwealth Club and World Affairs, I will say that science matters. We believe in the transformative power of science, and we're really delighted that you received and accepted the Distinguished Citizens Award. Thank you so much for your talk today, Deepak. Let's have a drink.
Let's have a drink.
Thank you.
Drinks on me.